All right, these are the final set of notes for Chapter 4, Linear Motion. Set this up in Cornell note style. Okay, here's your title. All of this, put that on the top of Cornell, and then don't forget your headings. Your first heading will be free fall. How far? How far? Okay, keep this in mind as we go. Okay. When we're dealing with free fall, every time, so you release the ball from this cliff height, right? You're laying on the cliff and you just drop it. Well, in the first second, it'll go this distance. In the second second, it'll go this distance. In the third second, it'll be somewhere way down there, okay? Each time it's traveling, every second, it's traveling at 9.8 meters per second squared, which means the distance between each second is increasing exponentially, all right? Each time it's increasing dramatically. That means if you were to take an average speed of it, of all the ball drops, and you just took the average speed instead of instantaneous speed, its average would be 4.9 meters per second would be the average. Okay, how do we apply that? Well, this is going to help us determine, because 4.9 is 1/2 of gravitational pull, or 1/2, 9.8 meters per second squared, okay? So, and then we know the distance is going to be exponential. Like each time the distance between the ball, like for every second the ball falls, the distance is getting exponentially greater, which means exponentially, for those of you who are unaware, is the exponents. It's squaring each time. So when we compile this, we get the equation distance is equal to 1/2 of the gravity's pull times time squared. There's your exponential. That's why on a distance versus time graph, you have this, when you have a parabola, this is considered an exponential, or, yeah, go back, exponential growth. Right? So when it makes that curve, it's called exponential growth. So it's moving up exponentially. So distance is 1/2 gravity times time. Okay. So if in any case I drop a ball off a cliff, I take the time, whatever time I'm trying to figure out. So I drop somebody off a cliff and I say, okay, at second 3, how far have they fallen? You could solve it by plugging in the time with the gravity and getting your total distance the object traveled. Okay, now hang time. You're going to read this while I set up the video. If you're doing this at home, you should read this and then click on the video that's linked in the Canvas notes. It's called Sports Science Hang Time. So now hang time is when you jump up in the air, like you're shooting a 3. You shoot the 3, you jump up in the air, and then you come back to the ground. You go up and you go down. Okay? That movement is called hang time. Now, it has to do with gravitational pull. All right? Gravity is slowing you down to a peak of 0 here, meters per second squared. Then you're coming back to the earth, quickly accelerating until you hit the ground. Okay? Well, in order to figure out how high you jump, you need 1/2 of your time, because if it takes you 0.8 seconds to go up and back down, that means half of your distance is 0.4 seconds. If the total 0.8, half is 0.4, and that would be like you jumping from a platform at whatever height that we're trying to solve, right? It would take you 4 seconds to get from your peak height to the ground. Keep that in mind. Okay, respond to these questions. They should be in your notes based off of what you watched. How long was this dude who we watched the video about in the air? Every time he jumps, what sort of graph does his body make? What was the time to the peak of his jump? What was the time the same to the peak as it was to his descent? Does hang time really exist? If not, or if so, What is it referring to specifically? Be specific. What is the max amount of time for the human to be in the air when they've jumped? Obviously, a plane is something different. And what is the reason for having a max hang time? Okay, Michael Jordan, best hang time he ever had on record is 0.9 seconds. That's the time his actual feet are off the ground. Now, let's round up to a second to make this math easier. And I told you, hang time is a little bit different than free fall because one, you're going against gravity, and then you're going with gravity. All we care about is the free fall component, this half. So, if this whole thing took 1 second, this took 0.5 seconds. So that's all we care about right here. All we care about is this. So let's work it out. Distance is equal to 1/2 gravity times time squared. Let's plug and chug our numbers. 1/2 10 meters per second squared times 0.5 squared, 0.5 squared. So keep showing your work. That's actually 5 meters per second squared times 0.25. All right, and now you have D equals 1.25 meters. That is the math that we do. Okay. Make sure you understand why I use 0.5 instead of 1. 1 would mean he jumped 5 meters in the air. Realistically, 5 meters in the air is like the height, at least the height of a one-story house, if not greater. Like, that's huge. Not really possible, not realistic unless you're on like some springs or jetpack. All right, let's see if we did this work right. That's what I got. Okay. 1.25 meters, about 4 feet. That seems pretty typical. Okay, now good athletes appear to jump higher, but very few can raise their center of gravity. A lot of times that appearance is because they're stretching their head to make the reach of whatever they're trying to do. So you stretch your body and your arms out to put it in the basket. Okay, so apple falls from a tree and hits the ground in 1 second. What's its speed upon striking the ground? So in 1 second, 10 meters per second. What's the average speed during this 1 second? All right, so at this time, his average speed, so speed is equal to distance divided by time. So you need to figure out the distance. So distance is equal to 1/2 gravity times time squared. So distance is equal to 5 meters. So now we have 5 meters. Your time is 1 second. So plug and chug. 5 meters, 1 second. It's equal to about 5 meters per second. We knew that. Okay. How high was the ground? Well, we did that. We already solved that. Here we go. Kind of went out of order, but there you go. All right. Side note, air resistance. Air resistance pretty much exists, even though we don't acknowledge it a lot in physics. So, affects things like light things or things with a lot of surface area. The bigger the object, the more it's going to flutter in it through the air. Same thing with humans. And eventually they'll hit a maximum velocity where, like, when I jumped out of a plane, I'm flying. There we go. Once the amount of air resistance going up equaled my acceleration going down, or my velocity going down, my acceleration, velocity going down, my acceleration equaled up to 0. Now, if there is no air, you will continue accelerating. Another thing, if I have a feather feather. Don't judge my feather. Or maybe it kind of looks like a leaf. And I have a human. And I drop them at the same time in a vacuum, which means no air. They're going to hit the ground at the exact same time. Weight, mass has no effect. It's just air resistance that determines the difference between the leaf and the human, or the feather and the human. Okay. Don't mix up how fast and how far. Remember, how fast is always 10 meters per second squared. Okay. How far is 1/2 gravity times time squared. Okay. Acceleration is rate of a rate, which means it's meters per second squared. So meters per second every second per second. That's formally what it looks like. This is confusing. It is hard. I trust that. Be patient. It will become easier. All right? Study up for the test, folks. Good luck.